Hey guys, my name is Tony Bechet. I'm your Physics 2C SI. Um, and yeah, that's kind of it. But so one thing I want to say before we get into this, um, don't there's nothing to worry about when it comes to physics. Just if you put in the time and effort, you'll definitely be able to understand these concepts. So I don't want to make this video too long, so let's just get into it. Uh, so first, um, I'm going to talk about simple harmonic motion. One more time, we're going to cover the conservation of energy, and then we're going to touch on waves, the speed of waves, direction of waves, the phase constant of waves, and then we're going to touch on sound, specifically intensity and decibel level. So, okay. So you guys probably remember these equations from physics 2A. So this is kinetic energy, this is potential energy. So an object in simple harmonic motion has both kinetic and potential energy. So I think there's a question like this on my worksheet. There's definitely one in the past worksheet where you need to take into account um, the speed of a wave, the speed of an object to find the mass. So I want to pose a question to you guys. Um, when does an object have the most potential energy? When does an object have the least potential energy? So think about this, and I'm sure you guys know this, but type your answer in the comment section. Okay. Um, and then we can talk about this during office hours. But something to keep in mind: when does it have the most? On a sine graph, on a sine curve. When does it have the most potential energy? When does it have the most kinetic energy? Okay. So another thing concerning waves, um, the velocity, the wavelength, and the frequency of a wave. How are they all connected? They're connected beautifully by this equation here. This is definitely something that you should commit to memory because it's going to pop up a lot of different places. So one thing I want to point out is that you're going to have questions on the exam, I'm guessing, where there's a wave traveling in one medium and then to another medium. So by medium, I mean some sort of environment. Uh, you know that the speed of air, the speed of wave in air or the speed of sound is 343 meters per second. Um, Commit that to memory as well. But the biggest takeaway from this is that the frequency does not change from medium to medium. So the frequency is the same. What does change is the velocity of a wave and the wavelength of the wave. So these are the things that are going to be altered, but the frequency is not going to be altered. It depends on the source. Okay. So I want to stress that frequency does not change. Okay, so let's get into what everyone's stressing out about. History and snapshot graphs. So before we get into this, let's define what each of them are, and let's have a clear understanding of what it actually means and why they're named this way. So when I think of history, I think of time. Specifically, we study something like we study politics over time. That's history. We study events over time, but the keyword is time. So when you're looking at a history graph, the x-axis is always going to have a time component. When you think of a snapshot, or when I think of a snapshot, I think of like a picture. Now, a picture captures a specific moment. It doesn't tell you what happened before. It doesn't tell you what happened after. It's just that moment. So when you're thinking of the snapshot graph, it doesn't tell you what's happening over time. It tells you what's happening at that particular point in time. So this is more like a picture, a snapshot graph. A history graph is more like a movie. Movie is a bunch of pictures put together. and it tells you what happens before and after. So that's kind of how I think of these type of graphs. Just before we even get into the whole um, conundrum, the whole situation. So the way I learn things is by steps. So um this will make sense when I show you, but I'm more of a methodical person. So when I see steps laid out in front of me, it's easier for me to understand. So I'm guessing some other people are this way. So we'll try this, and if it doesn't completely make sense, we can go over it more in more detail during office hours, Tuesday and Thursday, 2 to 3 p.m. office hours. I'll send out a link via email again. But so I'm going to be toggling back and forth between these two slides. So steps for determining the direction. So let's just take these one by one. So the first thing I do is I look at the history graph. Specifically, I ask myself, which point is it referring to? So let's go back. So before I say anything, which one is the history graph? Okay, history is talking about time. So this is a history graph. It is telling us that the snapshot graph is at x equals 0, or this is referring to x equals 0 for the snap. So when we look here at x equals 0, we're going to be looking here. Maybe that didn't make sense. when the history graph tells us it's at this specific point in time, we look at that point in time in the snapshot graph. Okay, so for instance, this is x equals 0. We're going to look at this point. If this said x equals 1, we look at this point. X equals 2, we look at this point. Okay, so that's the first step. Now the second step, look at the snapshot graph. What occurs at that point? And by the word occur, I mean as you move your eyes right, does the curve go up or down? So maybe confusing, but let's take it one step at a time, guys. So x equals 0. So we look at x equals 0, this point in time. So we move our eyes to the right. What happens to the curve? It increases. So we take a note. We say, okay, so it's increasing at this specific point. So let's say we were looking at x equals 1, and we move to the right. We see it's decreasing. Okay, x equals 0, increasing. So that was the second. Now, the third and final step, you look back at the history graph and then ask yourself this question. How does the curve on the history graph need to move to mimic the snapshot graph? Okay, so we look back to the history graph. How does this curve need to move to mimic this increase that we saw? It needs to move. So if this is so imagine yourself on the specific on the curve. Okay, like imagine yourself like you're actually on the curve. When we say move left and right, we don't mean the individual is moving. We mean that the curve is moving left or right. The person is staying on that same spot. So I'm gonna stand right here, and the curve is gonna move either right or to the left. Okay. So we see that there's an increase here. Okay, so we know that it needs to increase. How does this need to move so that it actually increases? If it moved to the left, we'd be decreasing. But if it moved to the right, we would be going up. So if we're standing here and this curve moved to the right, we would be increasing in amplitude. If it moved to the left, we would be decreasing in amplitude. As it moves, we're getting lower and lower, and then we're getting higher and higher. So when it moves to the right, we're increasing. So this wave is moving to the right. So another important thing is the determining the phase constant. So um, I feel like I have a good explanation of this in the first video. I might be wrong, but Um, anyways, let's try to touch on it a little bit. So when you're looking at the phase constant, when you're trying to determine what the phase constant is, do not look at the history graph. Do not look at the history graph. We're looking at the snapshot graph. If you want, so I'm going to say it again. If you want to determine the phase constant, look only at the snapshot graph. So the way I do it is I ask myself, how would I have to move? So, okay, I don't want to confuse anyone. Always compare this new curve, the curve you're trying to find the phase constant for, to an original sine curve. And then ask yourself this question: how would I have to move this wave so that it looks like the original sine curve? So how would you have to move this wave so that it looks like the original sine curve? We know that sine of 0 is 0, so an original sine curve would start here, and it would go up and down, up and down. So how would you have to move this so that it looks like the sine wave? Or another way you can ask it is, how would you have to move the sine curve so that it looks like this? To move, you would have to move the sine curve to the left a certain amount of degrees or radians. Now, we know we're moving it to the left. Oh, we know sorry. We know we're moving it to the left some type of direction. We're gonna have to move it to the left. We know this amplitude is 2. What value of sine will give us half of the amplitude? Pi over 6, right? So we're moving it to the left, pi over 6, and it'll give us half of the amplitude. So I think that should clarify any misconceptions. Please email me if it doesn't make sense. So let's get into sound. I don't want to make this video too long. So sound is denoted by intensity, how loud something is. And sound is power over the area. So power is the change of energy over the change of time, and area is, of course, area. So why is this area 4 pi r squared? So try to think of this, conceptualize this in your minds. When you're talking to let's say a friend, okay, has a friend has another person in the room like overheard you? Um, this is an explanation for how sound travels. So sound doesn't only travel in one direction the way we're facing. It travels in all directions, up and down, sideways. So this is the area of a sphere because the sound travels in a spherical kind of like dimension. So this is why it's like this. So two important intensities to always keep in mind: the threshold of hearing and the threshold of pain. So this is important for understanding how we coin or how we figure out decibel levels. So we see that this is I naught, this is IP. So I naught is 1 times 10 to negative 12. IP is 1 watt per meter squared. So when we look at decibels, we see that this is always the divisor. This is always the baseline of what we're basing every other intensity for. So if we're trying to find the decibel level for the threshold of hearing, this is I naught over I naught. This will give us 1. Log of 1 is 0. So that's why our decibel level is 0. Any other intent? So maybe like on a, I don't want to jump to conclusions, but usually on a test you'll be given a decibel level and asked to find the intensity. You'll be given the intensity and asked to find the decibel level. This is kind of, I think, I forgot, but I think I have a question like that on the worksheet. But these are just in decibel levels for various things that you probably wondered about, or maybe you haven't. But yeah, so that's all I have for today. Please use every resource you have to fully understand what's going on in this class. After you try my worksheet, write down any questions about concepts that you don't completely understand, and do your best to fill in the holes with what you're not completely understanding. And this is when you use Dr. Anderson's office hours, my Zoom sessions, your TA. This is the purpose of them, to fill in the gaps of your knowledge. So thank you guys for watching, and good luck with everything.